3. The final section is on device driver. And then we move on to chapter 4, the IP layer. After we introduce the link protocols, the point-to-point and broadcast links, and then which is the layer 2 mechanism to interconnect links together. So we try to interconnect broadcast links, broadcast domains together by bridging. So in a sense, we are separating broadcast domains by switches and VLANs, and then try to interconnect them together by bridging. And we have seen bridging is transparent in a sense that you don't need to configure anything. The bridges or the switches, the layer 2 switches, will do self-learning to know which port a destination MAC address belongs to. So we could tell by background self-learning, we know which port a MAC address belongs to. So once there is a frame destined to that particular destination MAC address, we will be able to forward to that port number. That particular port on the switch. So that's the self-learning in the background, and it's transparent to the stations. However, the self-learning might get confused if you have a loop if you have loops in the topology of the interconnection network. So we enforce a spanning tree by running the distributed spanning tree protocol, so that you would disable some port to form a tree. So there will be no loops in the logical topology, although there could be loops in the physical topology. Okay, so and we will see in chapter 4 the network layer could also do the similar internetworking to internetwork several broadcast domains together by the so-called routing instead of bridging. So you will compare bridging versus routing, which does interconnection at the network layer instead of the link layer. So we will see we will compare bridging at what situation we would use bridging, and at what situation we would use routing. Usually, the bridging is not as scalable as routing, because for bridging you would need to learn a lot of addresses, and if you need to learn thousands of addresses, MAC addresses, then you might explode the forwarding table. The bridging table will explode. So the number of entries will be too many for bridging. So bridging is not as scalable as routing. So it's only used in limited area. So for campus network, a small campus, okay. But for campus like this university, it would not work that well, because there are over 10,000 PCs, 10,000 computers on the campus here. And bridging would not, for bridging to scale to 1,000, it will be difficult. So bridging, as a way to interconnect broadcast domains or LANs, local area networks, then it's limited to small scale. So say within a building, okay, but across buildings, it might not be that scalable. then you would resort to routing, which is scalable. However, routing is not transparent. You need to configure. You need to configure the subnet, which we will see next in chapter 4. Okay, so after introducing this concept at the link layer, one final section is on the device driver. As we said that the link layer is mostly implemented in the hardware or in the device driver. So either in hardware or driver. And we have discussed at what situation you would implement in the hardware and at what situation you will implement in the driver. The criteria is if the protocol operation is time sensitive, then you put it into the hardware. If it's not time sensitive, then you put it in the software, in the driver. So we have seen that both Ethernet and wireless LAN, CSMA-CD and CSMA-CA, are both time-critical operations. So they need to be implemented in hardware without CPU involvement. Then in that case, the driver will degrade. They still need a driver, but the driver's function is degraded to just moving packet in and out. So the driver will be just a moving packet around, in and out. However, if the protocol operation is not time sensitive, like PPP, then the protocol will be implemented in the driver. So the driver will do the protocol operation as well as moving packet in and out. So the driver will do two things: moving packet in and out, and also the protocol processing, say PPP. Okay, so that's the. So in either case, the driver needs to move packet in and out. Okay, so the driver is between the hardware and the kernel OS. So you need to handshake with the OS kernel and also handshake with the hardware. So the interface between the driver and the hardware needs to be defined. So is the interface between the driver and the kernel. So, and we will see how this interface get defined and also get hooked. You need to do initialization. And also you need to do the interface could be either function calls or interrupt. So for example, as you will see that the interface between the kernel and the driver is a set of functions. So just function call between the OS and the driver. However, the interface between the driver and the hardware will be in the incoming direction. It will be interrupt. So the hardware needs to generate interrupt to get the attention. To get the attention from the driver. So once there's a hardware interrupt, the CPU control is passed to the one interrupt service routine, and then interrupt service routine jump to the driver, the parts that handle the interrupt within the driver. Okay, so that's the way you get the attention from the driver to handle the job. And for the driver to interface with the hardware, it needs to know the so-called data sheet of the hardware. It needs to know the address of the registers, where the registers are. You need to program the register, rewrite the register in order to issue command to the hardware, or read the status from the register. Okay, so all these rewrite with the hardware will be to to or from the registers. And where the address of the registers are documented in a document called data sheet of the hardware. Usually, the hardware manufacturer would have a data sheet specifying the addresses of these registers. Okay, so these are their interface. So we will talk about the concept of device driver first, and then how to communicate with the hardware in a device driver, especially in Linux. And then we'll see a real example in the Linux device driver for Ethernet, which is for Ethernet. And similarly, you can see the device driver for wireless LAN. It will be almost the same because, as we said, that Ethernet and wireless LAN, they both have their protocol implemented in hardware. So the driver for them is only for packet moving in and out. Packet moving in and out. Okay, so they'll be the same. Okay, so for the driver, it's between the device and the OS kernel. Okay, there's a piece of program that understands the device, the hardware. And as a programmer, you would need to know the interface between the device driver and the device. And an interrupt handler is something between the hardware interrupt and the driver that is registers for a particular number of hardware interrupts. So if the driver, if the hardware has a hardware interrupt number of 3, say IRQ, interrupt request. IRQ stands for interrupt request. Number 3, then you need a handler for number 3, interrupt number 3, hardware interrupt number 3. And this handler, once there's the device generate hardware interrupt number 3, it will be the control of CPU will be switched to this handler. And again, the handler would then will call the driver some certain function in the driver. So then the control is passed through the driver. So interrupt handler is a tiny program that is only to use to accept or intercept the hardware interrupt. And it's small, and it will pass the control to the driver. Okay. And if a device has something to tell the driver, it would need to go through the interrupt handler. However, if the driver it has something to tell the device, it does not go through the interrupt handler. It would just go to the device to program the device registers directly. So for this direction, for hardware to tell something to the driver, it would need to go through the interrupt handler. But for this direction, for the driver to program the hardware, it would not go through the interrupt handler. It would just program the hardware directly, program the register directly. So that's the difference. So if from the aspect of the driver, it passively waiting for the interrupt from the driver. But in the active part, it program the registers. It would not need to go through the handler, interrupt handlers. So there's a subtle difference here. And for the interface to the OS, there will be function call here that you can call the OS. And again, OS would have a set of functions to call the driver. So there'll be a set of functions within the OS to be called by the driver, and a set of functions in the driver to be called by the OS. Okay, and you will see those common functions in our later figures called graph. Okay, and then there'll be interface between the OS to the user processes, and these interfaces are called system call. So as an application programmer, you commonly call system call to get service from the kernel, from the OS. So something like a socket read write, these are system calls that you ask the kernel to do something. Okay, so this interface here is system call, and there's no clear name here for this interface. And the interface here. There's a classical interface called NE2000 network. NE2000 Novell. I think NE. I don't remember the abbreviation stands for. It's called NE2000. It's developed by Novell, and it defined basically it defined the address for the registers, so that you don't need to write. You don't need to modify the driver as long as the device is NE2000 compliant. NE2000 compliant means that the register, the address of the register are fixed. So the driver would access those registers in the same way as other NE2000 devices. So if this driver is for this device, which is NE2000 compliant, and there's another device which is also NE2000 compliant, then I can port this driver from here to here, and the driver is supposed to work smoothly. So then the driver portability will be high if everyone complying to NE2000. However, NE2000 is too limited, too simple. Most devices become more advanced. So then it doesn't make sense to have a limited capability or limited data sheet in a device. So then the manufacturers start to do something exceeding NE2000. So now the driver, if you are a driver programmer, then you don't expect NE2000 device. What you do is you just read the data sheet of the hardware in order to know the addresses of the registers and their meanings, their definitions. So you read the data sheet and then program. Okay. So the interface here is documented in the data sheet, and here it's a quite limited interface, quite limited function calls here, and system call here. Okay, so for the driver to communicate with the hardware, it need three mechanisms. You need to probe I/O port, meaning you need to map the register to a region of addresses for read and write, meaning that you need to know where the registers are. And actually, when you write the register, it's more like doing I/O on some port, on some I/O port. So you need to writing to a register or reading from a register is the same as I/O. input and output on particular I/O port. So here you want to know the numbers, the port number that will map to those registers. So you need to probe that. And then once you probe that, you need to bind or register the port number for those address register for those registers. So that's the first thing. And then you need to bind the interrupt handling. Okay. So interrupt is an asynchronous an interrupt is an asynchronous event to get CPU attention, and you need a handler which will be invoked upon the interrupt generation. So as a driver, your interface with the device will be two things. In this direction, downward direction, you need to know the port number, I/O port number, that will map to the registers of the device, of the controller of the device. Actually, there will be a controller on the device. And then in that direction, in the upward direction, you need to register. You need to register the interrupt handler for a particular hardware interrupt. Okay, so these two are two directions. One is the first one is downward, and the second one is upward. And then you need to have a third mechanism called DMA to move the packet in or move the packet out. So the DMA will do the packet moving from, say, for example, from the interface card, adapter card of the device, from the device to the memory. Okay, you have memory, your motherboard here, and there's another board which is the adapter, the device. So you need to copy the packet from the device to the memory in the motherboard. And also you need to copy, you might need, for the outgoing packet, you need to copy from the memory to the device. Okay, and you don't want this to be done by CPU, because if CPU is doing the job, it would take time. For example, if you have a packet of 1500 bytes, 1500 bytes, and if each memory copy is 1 byte, then it would take 1500 instructions to move the packet if it's done by CPU. So it's very inefficient if you do that. And direct memory access is a mechanism that you can move data around, in and out, without CPU intervention. Okay, and that's done by DMA, the hardware. So it efficiently transfers a large batch of data to and from memory without CPU's involvement. Okay, so the driver will do what? Will program the register, say, write a command to the I/O port, which is to write the register, and tell the register, okay, tell the device, I'm telling the device, okay, I have a packet in my memory. Here's the address. I tell you the address, and you need to move the packet from that address to your device, and you need to move how many bytes? Say you need to move 1500 bytes. Okay, so I tell you two things. One is where it is, the address in my memory, and how long, how many bytes. Okay, and then I'm done. I tell you, I write this to the register, and I'm done. The driver finished the job, and then the CPU control is passed to something else. And then DMA will do the job to move the packet from the frame or the packet from the main memory for so many bytes and copy to the device. And within the device, for sure, there's a buffer space in the device to store the frames to be transmitted. And then once the DMA has done the job, has finished the job, it will generate a hardware interrupt. It will generate a hardware interrupt. And again, there'll be a interrupt handler, right? For example, if this is hardware, if this generates a hardware interrupt number 3, meaning IRQ number 3, then the interrupt handler for IRQ number 3 will take the control of the CPU, but it immediately pass through the driver, certain function in the driver, and that function will do what? The driver will then read the register. There's a status register on the device, so it read the status register to see what's going on. So you interrupt me, I need to read your register to know, okay, what has happened. And when it read the status register, it would know, okay, the device has transmitted the frame successfully. Okay, has finished moving the packet and then finished transmitting the frame successfully. So the device, the DMA, after moving the frame, it will go ahead to transmit the frame. If there are multiple frames in the queue of the device, it would transmit them one by one. And after it transmits the frame successfully, it would generate an interrupt. So you would say we could generate the interrupt after moving the packet, but before transmitting the packet. But then it would introduce one more interrupt. So instead of interrupt the CPU right after you move the packet from the main memory to the device, you wait until the frame is successfully transmitted. So the DMA does the moving, and then you run CSMA-CD or CSMA-CA to transmit on the link, and if it's successful, successfully transmitted, then you generate interrupt. Okay. However, if there is something wrong in the process, you also generate interrupt, but you specify what happened in the status registers. Okay, so that's the process. So that's the DMA's job to move the packet without CPU involvement. Okay, so how do we read from registers? So actually, if you want to read something, read from the register, or read or ask a DMA to read something in. Okay, the first thing is that you read the register from the device on the device with the instruction, with the command of this IMB. You read the registers. Usually this is you want to read the status register. You want to know what happened, so you read the register, and you specify the port number, which is the port number for that particular register. Usually, as I said, usually it's a status register, and you need to know the port number for that status register. So again, the registers on the device are all mapped to I/O port numbers. They are all mapped to I/O port numbers. So here you specify the port number. Essentially, you are specifying which register you want to read. Okay. And you may also want the DMA to read the the frames in. Okay, so you specify that you want to read from a particular port number, and then from a particular device, and then you specify your internal memory address space. So this is your address space in the memory. Okay, for how many bytes? For how many bytes? So I'm telling DMA, okay, I want to read from this device and into the memory at this address, and for so many bytes. Okay, I think this will be a return value. It's not an input; it will be an output. Meaning, once this function returns, I can check this number, this variable, to know how many bytes the DMA has moved in. So I issue this, and telling the DMA to read from a device to a specified memory address. And in the outgoing part, if I want to write something, so for reading from I/O port, I'm mostly reading registers, status register, to understand the status. But for writing to the register, I'm writing commands to the register. So I'm issuing commands. I'm asking the device to do something. So I issue the command to the register. So I issue this command to this port number, and this will be the address of the register on the I/O port. Okay, for DMA, I want to write something, and that data is here in my memory. So I'm telling DMA, I want to write this, move this out, and the data is here for so many bytes, and I want to write it to this port number, which is for a particular device. Okay, so when I issue this, I'm telling the DMA to move the data out. And here I'm issuing command. Okay, and there's in all textbook in operating system, it specify the procedure to for interrupt handling, and here is what happened in almost all systems. First of all, there's a hardware interrupt. When there's a hardware interrupt, the hardware itself will stack, the CPU hardware itself would stack the program counter, PC program counter, which is the most important register within CPU. And it's done automatic by the hardware once there's a hardware interrupt. And then the hardware will load the new program counter from interrupt vector. So if this is IRQ number 3 from hardware number 3, the interrupt IRQ number 3, then there's an interrupt vector, and the third entry will point to an interrupt service routine. So I would the hardware will take the interrupt vector entry number 3 into the program counter register of the CPU. Okay. The interrupt vector is stored in the memory, somewhere in the memory. So what the CPU does is it would grab from memory particular space to grab the interrupt vector entry number 3, and perhaps there's a 32-bit address there, in the entry number 3, and I will load it to the CPU into the program counter. Okay, and when you do this, it means that you pass the CPU control to the interrupt service routine for IRQ number 3. And then there's a within the interrupt service routine, it's written by assembly language for that machine. Okay, for that CPU. Suppose this is Intel Pentium, then it uses the assembly language. In the interrupt service routine, it's written in assembly language, and the assembly language procedure within the interrupt service routine would do what? It would do some housekeeping. It would save the register because within the CPU, it was doing, before the interrupt, it was doing something else. Okay, and that something else, the intermediate result of that something else is in the status of that something else is in the registers. So you need to stack the registers. So just like you stack the program counter, you also need to stack the other register. A program counter is only one of the registers, and stacking the program counter is done by hardware, but stacking the other registers is not done by the hardware. It's done by interrupt service routine in assembly code. So you would save the other register values to the stack, and the stack is in the memory. Again, it's in the memory, so I need to stack. So I have stacked program counter there. Now next I need to stack the other registers, and then set up a new stack, because I need a new stack for the new thing. The previous thing has been stacked. Program counter and other register have been stacked in the memory stack, right? Okay, but I need to establish a new stack for the next thing I'm going to do. So I have a new stack set up, and it's done by interrupt service routine. And then once this is done, the interrupt service routine will pass the control, will call the driver, a certain function code of the driver. And then how does the interrupt service routine know which function to call, or where to call, where to jump to? It needs to register. So your driver needs to register to the interrupt service routine. So I need to register the driver before I can do this. I need to register the driver to handle, say, for the interrupt IRQ number 3, I register the driver. Okay, so if I have registered that driver, then after the interrupt service routine has handled this, it will then pass the control to the driver. And the driver is mostly written in C language. Here the driver will do the real thing to process the interrupt, and then after it processes the interrupt, awaken the sleeping process. The sleeping process is the process that was interrupted. So you have interrupt, and the CPU was doing handling the process. It was serving the process, but it was interrupted. So you stack the process to the stack. And then after you have done the job, you have handled the interrupt, the driver will need to awaken the sleeping process. And then the assembly code in the interrupt service routine would also do the remaining job to start up the process that was interrupted. Okay. So between step 3 to step 6 is controlled. It's handled by interrupt service routine, except step 5, which is done by the driver. Okay. Okay. So and there's a tricky part is that within the interrupt service routine, there could be two parts. There could be one part or two parts. If the if the interrupt can be served quickly, then you just need a one part, the fast handler. However, if it takes longer time to handle the interrupt, to process interrupt, then you will break down things into two parts. One is the fast handler, one is the slow handler. So let me give you an example. If you are in the office and someone drop by to interrupt you, and then you will be interrupted, and then you want to serve the person who interrupt you. And if the person is only to ask you one simple question, say, when are we going to meet tomorrow? Then you would answer, okay, tomorrow 3 p.m. So that's a done deal, right? So then if you want to write a driver for this part, for this interrupt, then you would just mount the driver in the fast handler. You just need the fast handler. If there's another kind of interrupt which needs you more time to handle, for example, someone drop by to your office and asking, I have a question. I don't know how this entire section is talking about. So can you explain the general idea about this? Then you realize it's gonna take 15 minutes at least to answer his question, to explain the section. Then what? Then you will tell this guy, okay, I don't have time now, but can we meet tomorrow at 9 a.m.? Okay. So what happens is that it interrupt you, come to you, asking for a big question, which would need 15 minutes at least to answer, and then you would tell him, okay, come again tomorrow at 9 a.m. Then then tomorrow morning at 9 a.m. you will actually spend 15 minutes to answer the question. So the service time is decomposed, is separated into two parts. One is the 30-second meeting arrangement. You spend 30 minutes to talk with him to arrange, okay, that'll be tomorrow 9 a.m. and then he's gone. But he will come again tomorrow 9 a.m. for 15 minutes for discussion. So the interrupt service will be broken down into two parts. And the first part will be mounted on fast handler. The second part will be mounted on the slow handler. And for the fast handler, you will do it immediately. For the service, the driver will do this thing immediately. But for the part in the slow handler, it'll be done later. But what is later? How late is later? It'll be done when there's a chance for that. When there's a good chance for that. Okay. And within the fast handler, and it will be different from the slow handler. For example, this could be a very short time, and this will be longer time. So the mechanism within fast handler and slow handler will be different in terms of the interrupt reporting and servicing. For example, here you say in a fast handler you would disable all interrupt. So I'm handling for interrupt IRQ number 3. I'm handling it. When I'm handling it, no other devices can interrupt me. So I'm disabling all hardware interrupt. Okay. And then I also I also disable interrupt being served. Well, this sentence is kind of redundant because I have interrupt from 1 to 8, and I disable the interrupt reporting mechanism for all of them. And the second sentence say that I disable interrupt number 3, IRQ number 3. I also disable that. So I'm disabling all interrupts, hardware interrupt, and then I do the job. After I do the job, I'm done. So then I enable the hardware interrupt. However, in the slow handler, because I'm going to be here for quite a while, so if I disable all hardware interrupt, it will be a problem. It will be a problem. See, I'm going to discuss with you for 30 minutes, and I shut the door. No one can interrupt me. Even my wife couldn't. Then it'll be a problem if I stay here for 30 minutes without answering the interrupt. So I can disable all interrupt. I would just disable interrupt, say number 3. I disable this device, particular device that generate interrupt IRQ number 3. It would not be able to generate another interrupt again. So I disable that. However, I enable all the other interrupt mechanisms from 1 to 8 except number 3. So all the others are enabled. So they can interrupt me while I am in the slow handler. And the reason why we are doing this and this is because here we are going to stay here for quite a while. And for the quite a while, it means perhaps hundreds of microseconds. But here it will be probably less than 1 microsecond. Here you stay, say, tens of hundreds of microseconds. So you couldn't disable all interrupt. You would enable the other interrupt. So it's possible that you would have a nested interrupt, meaning I'm handling interrupt number 3, and I'm in a slow handler, so I do not interrupt. I do not disable all the other interrupt. So when I'm in the slow handling of this interrupt number 3, I might be interrupt again, but not by IRQ number 3, but by something like IRQ number 5. So number 5 can interrupt me. So what would happen is that I would stack the handling process of number 3 to the stack, and I would handle the IRQ number 5 first. So the interrupt handling might be nested. Okay, in this situation. So then you would ask, when are we going to put the driver in the slow handler? Okay. So if the driver needs to do more checking, so for example, in PPP, remember in PPP we not only move the packet around, we also do protocol processing, right? So the service time will be longer. So you will put that in the slow handler. However, if it's just read the register or issue command to DMA, then it'll be fast. Then you would just need a fast handler. And for Ethernet and wireless LAN, because you don't need to do protocol processing here, you only move packet around. So you would just need the fast handler to, you would just register your driver to the fast handler. However, for PPP protocol processing, you would, because the driver does protocol processing, a lot of processing there, so you would put it into the slow handler. You would need a fast handler and also the slow handler in the case of PPP implementation. Okay. So the general guideline for implementing an interrupt handler is you would need to know what kind of interrupt it is. Say packet arrival, transmission complete, and then you need to awaken the process sleeping on the device, and you also need to watch the service time. If the service time is short, then you just need a fast handler. If it's not, if it's longer, then you need the slow handler. And the slow handler are usually called the bottom half. The bottom half. The slow handler, the top. Well, so if you split your driver into two parts, one is to register to the fast handler, one is to register to the slow handler. Then this is called the top half, and this will be called the bottom half. Again, you need to register your driver to the handler. And if you split your driver into two parts, then these two parts, one is called the top half, and the other will be called the bottom half. And the top half needs to be registered to the fast handler. The bottom half is registered to the slow handler. And then the fast handler needs to be registered to the kernel, to the OS. Both fast and slow handler. So again, it's a hierarchical relationship that you have the driver invoked by the handler, and the handler registered to the kernel for a particular in the interrupt vector. So the handler is registered to the kernel mounted on interrupt vector. Okay, so it's a hierarchy relationship here. Okay, we have explained the bottom half, top half, and how to use bottom half. If you have a driver that needs to be registered to the bottom half, you use these functions. You use this function to register. For example, this is a driver function that you register to be a part of the bottom half. To be a part of the bottom half. And then you need to, so your driver is registered by this. Your driver is registered to the bottom half or the top half. And for your driver, for your handler to register to the kernel, so that the kernel will be able to map the IRQ number to a particular this interrupt handler. So you also need to register your interrupt handler to the kernel by this function. So you request IRQ. So I would say the IRQ number 3 is handled by this handler, and I need to register this information to the kernel. And once you issue this in the initialization process, the IRQ number in the interrupt vector, it would fill up the address of the handler. The address of the handler to the interrupt vector for IRQ, say number 3. Okay. So here here's an open source implementation that where you can see the actual function used for these three different things. We have mentioned that you need to probe I/O port in order to know where the registers are. Register of the devices are. Again, you need to differentiate the register on the device and also the register on the CPU. It's different. On the CPU, you have register, program counter, and other registers. On the device, you also have register, and those registers are the interface between the hardware and the driver. And again, those registers are mapped to I/O port. Okay. So here, you are actually checking, requesting the I/O port. Okay. And then you need to probe the IRQ. So see, the driver give an order to device to produce an interrupt and then check the information. So so I would during the initialization, I was issued this call this function, so that to ask the device to generate a hardware interrupt. Okay, for a check. I want to check whether the device can generate interrupt and I can handle the interrupt successfully. So you need to probe that. And then it is supposed to generate an IRQ, a hardware interrupt, and then the control will be through the interrupt service routine. And then since I have registered to the interrupt service routine, the interrupt service routine will call this driver. Okay. And then the DMA, to access the DMA, during the initialization, you need to call this function, which is DMA map single. So you're mapping the DMA in the initialization. Okay, so for the driver, with the device, when the data frame comes in, it will be just a frame. However, the driver needs to transform this data frame, packet frame, into SKB buff. SK buff. This is SK buff, which we have discussed in chapter 1. In chapter 1, the final section is we have discussed the data structure of the packets. And here the driver needs to prepare the SK buff from the pool of SK buff. And then a frame will be stored in the SK buff. Well, actually, you don't do memory copy. You just prepare a structure of SK buff, and then let the structure point to the frame here. So actually, you prepare an address. You have allocated an address at first, and then you do DMA. So the DMA will move the frame in here in the memory, but it's a frame. But you still need a SK buff structure in order to manage the frame. So I would have a SK buff structure that will point to several pointers, point to the frames, to the frame. Different spot of the frame will be pointed by the pointer here. And I can join the queue by modify the pointer here. So then the frame will join the queue. Okay, so this is the frame mounted on SK buff. Okay, we have talked about the escape path structure, that it would have a certain pointer to point to other escape path, and here there'll be pointer to point to the actual frame. So the actual frame is not stored here; it's stored at some other address, but will be pointed by the pointer here. Also, there'll be a structure for device to describe the device. So I would describe the device, say the IRQ number. I will specify the hardware address, which is the MAC address, and MTU. So these are some attribute of the device specified in net device. Okay, the final one is on the final open source implementation in this chapter. That's a that's a real device driver named as NE2000 2K -PCI.C. Okay, so that's the real program. And within this program, it does initialization, and it also handles three-part initialization, transmitting, and receiving. That's for the initialization. The driver, we have seen that the driver needs to talk to the kernel, register to the kernel, and also need to probe the hardware. And we have seen here you would need to do this. You would need to call these functions to probe the I/O port, probe IRQ, and initialize DMA. So that's probing hardware to get I/O port and also the IRQ number, and register and also set up the interrupt handler. Okay, for transmission, here's what happened. Transmission, you would the frame will be from the kernel. The frame to transmit will be from the kernel. So the process, transmission process, for the driver, the transmission process start from the kernel. So the kernel will call this function, which this function in turn will call this function here within the driver, and then it would call this function to it will call this function and this function to do the DMA, to issue command to the DMA, and then and then the driver is done. The DMA will do the job to move the packet, to move the frame, and then the device, after moving the frame inside the device will start to send the frame. And if the frame is sent successfully, it will then generate an interrupt. So as we say that after you finish the DMA, you don't generate an interrupt right away. You would generate interrupt after you transmitting the frame. After you finish transmitting the frame. So what happens is that you generate you do DMA and then transmission, and then generate interrupt. So the interrupt is generated here, and then there'll be the control will pass through the interrupt handler. Depending on have interrupt handler register on the interrupt service routine. I mean, register on the interrupt vector. Okay, and then the interrupt handler will pass the control here after finish the housekeeping job that we have mentioned. It's done by assembly code, and then the control is passed through the driver here, which is written in C, and then it would do this. Here it would do. It would check what happened. It would read the register, status register, to see what happened. If it says that the frame is sent successfully, then it's a done deal. And then it would check whether there are more frames to send. If there are more frames to send, I issue the command to send the next frame. So it's in the sense that I ask the DMA I ask the device to move the frame and also transmit the frame. And after it has finished the job, it generates an interrupt. And I will check whether it has successfully transmitted. If it is, and I have more frame to transmit in my buffer, then I would issue another command to transmit the second frame. Okay. And then the device would again move the frame and then transmit the frame. So here, but if I don't have another frame, if I have only just one frame and I have no more frame to transmit, then after I finish reading the register and seeing and knowing it was a successful transmission, then it's a done deal. I would not transmit another frame. So that's the process. For receiving, the receiving process, the device has some frame coming in. So first of all, it would generate interrupt. So these two figures, the first step start at different spots. Here it started from the kernel, that called the driver. Okay, so the frame is from the kernel. But here the frame is from the device. It's incoming from the device. So first thing is to generate interrupt. So interrupt occurs here, and then the control is passed from the interrupt service routine, the handler, to the driver here, and then it would call this function, and then this function to check what happened. Okay, it would check. Okay, this is a frame arrival. After reading this, it would know. This function will know. Okay, this is frame arrival, and I need to tell the device where to move the frame in. I need to tell the device where to move the frame in. So what I would do is I would prepare a data structure, a space, and then program the device, I will program the device with this command, with this function. I will tell the DMA, okay, I have prepared the data structure here, and please move in your frame into this memory address. Okay, so I'm telling the DMA to move in the frame to a particular address, which I have allocated the memory space. Then I'm done, And then what happened is that I would then wait. Well, I'm done. The driver has done the job. However, the frame is not in yet. Then the device will do the DMA. The DMA will start to work to move the frame into the memory. And after it finished the job, copying the frame into the memory, it would again generate another interrupt. And then it will come through here again and saying, okay, this interrupt says, I will read the register, and the status register tell me that this is not a frame arrival event. This is a frame transferred event. The frame has been transferred into my memory already. Then so the frame is in my memory already. On the first interrupt, it was not in yet. On the second interrupt, it was in my memory. So then I will call the kernel, passing the frame to the kernel. So, but it would prepare the data from escape buffer. It will prepare a structure of escape buffer, and then manipulate pointer to point the frame, and then mount the escape buffer to a queue in the kernel, and then call the kernel function, notifying the kernel function. Okay, I have a frame passing to you upward. So I'm passing the frame to you. So if you have, so you immediately find out that you need 2 interrupts in order to receive a frame, right? But you just need 1 interrupt in order to transmit a frame. Okay. The reason why you need 2 interrupts for receiving is because on the first, the event is the interrupt the status register tell you it's a frame arrival, but the frame is still in the device, not in the memory. On the second interrupt, the status is frame transferred. The frame has been transferred to the memory already. It's lying there. It's in already. So you need 2 interrupts. However, for the transmit, you just need 1 interrupt because the interrupt is telling you the frame has been transferred, has been DMA'd, and also transmitted successfully. So you just need 1 interrupt. So that's the difference between these 2. Okay, this is performance matter sidebar here that tell you the overhead, the time required for interrupt and DMA handling within a driver. Here the interrupt handler, the receive and transmit, they approximately take the same amount of time. However, the DMA time is different. That if the frame size is larger, then it would take longer DMA time. But again, this is not the CPU time. The DMA time is not done by the CPU. It's the collapse time. It's the collapse time, the time it takes for the DMA to work. But since it's not done by the CPU, so it's not CPU time. Here it is the CPU time. Here it's the CPU time, but it's the DMA time here, not the CPU time. And okay, so here the time, DMA time is getting longer as the frame size gets larger.